Welcome to this short recorded lecture for Lecture 4 of Math 5027. So the focus of this lecture is on subsequences and their relationship to what they call the mother sequence. So that's what's in this first theorem. He calls it the mother sequence. So I think one thing from this initial paragraph that you should really get out is that you should consider that a subsequence is like a composition of functions. So if you think of P sub n sub k, then you should really think of it as P of n of k. That's what I'm writing here, right? Because I tried to describe before that sequences are just functions that map the natural numbers into the metric space that you're in. Each natural number corresponds to some point in the metric space. So now n of k is just a strictly increasing function that maps the natural numbers into the natural numbers. It's not necessarily onto. So the idea is that you're just picking in order some possible subset of the original terms in the first sequence, then what they call the mother sequence, which in this case is denoted by P sub n. And so they have to appear in the right order, and that's why that you have the strictly increasing function requirement on n of k as a function from the natural numbers into the natural numbers. So then with that perspective, they have this theorem about how should you prove that every subsequence of a convergent sequence has to have as its same limit the limit of the mother sequence that converged. So there's this proof that's quite short that's given in the book that I put here. And my suggestion was that you should rewrite the proof using our language for the 4 steps based on a definition. And so I just show it here. There's actually not a whole lot to it. You should try to do this on your own. But if you need help, you can pause this video and look at it. And I just made it really clear like how to write out the 4 steps that the structure of any proof based on the definition of convergence of a sequence has to have. So the first thing is I say let P sub n sub k. I don't like this Q sub k notation that he uses. Let P sub n sub k be a subsequence of a convergent sequence. P sub n that converges to P in the metric space M. So now that you do that so that everything's defined that follows. Their first and third steps of a proof based on the definition of convergence are always the same. Let epsilon be greater than 0. But now instead of let n, little n be greater than or equal to n, in the third step you write let k be greater than or equal to n. Because k is the index that denotes the term of the subsequence you're talking about. All right, so that's kind of key. And again, you use the strictly increasing aspect of that function n sub k to know n sub k is something that's greater than or equal to k. And that's kind of the key point of this proof. So I'm not going to read everything to you here. It's actually pretty simple for you to just pause this video, read this yourself, fill in the details. But I'll take questions about it in class. But it's something you should really sit with in terms of understanding what's going on in this proof. Make sure everything's crystal clear. All right. Now, I ask you on this next page to prove that the alternating sequence, -1, 1, -1, 1, this sequence defined here. In fact, that's actually really bad notation on my part. I should have written it like this. It's -1 to the n. Like to make sure it's a sequence, I need to put parentheses around that. So you should fix that in your notes. You should put this outer set of parentheses that I just added on there to correct the notation that I hand wrote there. So with that problem, my hint is you could use theorem 1. And the take home from this is that's a really useful theorem, this theorem that was proven on the previous page. It's really useful to use that theorem to prove that a sequence diverges by showing that you can find 2 subsequences that have different limits. Because if you can do that, then by theorem 1, the original sequence can't converge. Because if it did, all subsequences would have to converge to the same thing. So the moral of the story is, if it is easy to identify 2 subsequences with different limits, then, excuse me, that's what you should usually do to prove that a sequence diverges rather than try to negate the definition of convergence. However, that's always an option. You can always negate the definition of convergence. That's something that will always work. Now, that's the pro. The cons are the details can be quite tricky. It often requires several cases since the first step of a proof is to let a point be in the metric space. And then you have to choose an epsilon somehow. And that epsilon that you're going to have to choose often is going to depend on P. Try doing that for this problem. Try using the negation of the definition of convergence. And you're going to have to do 2 cases. You're going to say like, well, let S be some real number. And you're going to have to show that no matter what number you picked, -1 to the n doesn't converge to it. And if that number is positive, you might choose epsilon one way. If it's negative, you might choose epsilon another way. Or you might have to have some details change. So it kind of depends what you do in terms of what the point is and what you choose for epsilon. Later, we'll also see that convergence implies Cauchy. If you remember what Cauchy sequences of real numbers are, there's natural extensions of that notion to arbitrary metric spaces. And as soon as we have a theorem that says convergence implies Cauchy, which we'll get to soon enough in this class, then you can also just show a sequence is not Cauchy. So that has the advantage of that you don't need to construct some point, or you don't have to let P be any point. You just have to show that basically the points in the sequence don't kind of get and stay close to each other. Meaning you only need to choose an epsilon such that no matter which point in the sequence you pick, you can always find two indices at, farther, at least as far out as that n, that index n, such that the distance between them is greater than or equal to epsilon. We'll see that later. So this is just a little foreshadowing, but I would suggest try using theorem 1 and try using the negation of the definition of convergence to prove this result. So on the next page, this is kind of an application. It's that previous problem on the previous page is useful in this one. So again, you should try working that one out on your own. The details are pretty straightforward from elementary analysis. This is an interesting problem. If you let P sub n be a sequence and f is some, and here I'm just making it clear, like I'll say in a metric space X, and f is a bijection from the natural numbers to the natural numbers. So that means it maps into and onto, and it's one-to-one. It's one-to-one. Okay, let's make it simple. It's a one-to-one mapping from the natural numbers to the natural numbers. Then defining a sequence Q sub k. Now here's a good use of the notation Q sub k. P of f sub k, f of k, is some rearrangement of Pn. So the idea with this is a rearrangement is not all the terms in this isn't a subsequence necessarily, because the terms don't necessarily appear in order. And so they ask in part A, are the limits of a sequence unaffected by a rearrangement? I think you should think about this problem on your own. I just give you kind of a key here. F is a bijection. So meaning if you talk about Q being like 1, 2, 3, 4, 5, so on, and like out to 50, F of K might be the following. It might be 50, 2, 4, 10, 3, 1, and then maybe the 50th term in your subsequence. So if K, or not subsequence, rearrangement. The 50th term in your rearranged sequence might be the 100,000th term from your original sequence. And then way out at some point is maybe like the 11th term of the original sequence shows out some point later. So you should ask yourself, are limits of a sequence unaffected by rearrangement? So my hint to you is kind of, well, I'll just give you the answer. No. If a sequence converges, then the rearranged sequence also converges. Now, what I've shown here is to maybe get you started with the idea of if you need f of k to be greater than or equal to 50, then what type of capital N, how far do you need to go out such that if k is greater than or equal to n, you can always say that you're grabbing terms from the original sequence that are also greater than or equal to 50, right? Because here, like, I could be talking about k, in this case, maybe the k that corresponds to this is equal to, like, I don't know, a billion, 10 to the 9th, okay? Then how far would I need to go out to make sure, like, let's say that 11 was the last term from the 1 to 50 that showed up here. Like, it has to show up at some point. So I need to go out at least to the billionth term in order to make sure that in my rearrangement, all my terms are at least the 50th term or beyond. Even though the 50th term shows up here, the second term shows up here, and so on. That might seem really confusing. You need to sit with that. You might need to rewind what I was just saying and watch it again. But this is a good problem to really think about, and think about what happens if this changes, if F is an injection or surjection, if your answers change. This is such a great problem, exploring the definition of properties of convergence for abstract sequences. So this was actually something I gave as homework assignment last year. I give this to students a lot in analysis, so it's for us to work on in class. You should try to fill in the missing details. So the basic idea is the following. If you can prove that for a sequence Pn, if there exists a P that's the same, such that for any subsequence P sub nk, there exists a further subsequence, a subsequence of the P sub nk, that converges to P, that means the original sequence has to converge to P. So again, what we're saying is, you're not claiming that the subsequence converges, although that's a consequence of this. You're saying is, no matter what subsequence you construct from your original sequence, you can always find a further subsequence of it that converges to P. That can only happen if the original sequence converged to that point. This result gets used to generalize so many other results. It's such a great problem. It can simplify a lot of things. So I really suggest you do it. I kind of started the proof for you here. It's about it's a proof by contradiction. I'm asking you to fill in the details. So you can pause the video, try to write some of this down. The basic idea is that you start by choosing a point P such that for every subsequence of the original sequence, there always exists a further subsequence that converges to P, right? That's what this says right here. So as soon as you have that, then I'm assuming to the contrary that the original sequence Pn doesn't converge to P. And what that means, I'm saying what it implies to set up the structure of the rest of this proof by contradiction. That means there has to exist an epsilon such that no matter what index capital N you pick, you can always find a term in your sequence at least that far out such that the distance between Pn and P is greater than or equal to that epsilon. This is just a logical negation of the definition of convergence. And then when you do that, I'm negating the definition. There's this there exists. I'm going to choose such an epsilon that has this property. And then I use this negation of the definition and this specific choice of epsilon that satisfies this to inductively construct, which you have to finish off, a subsequence P sub n sub k, where every single term is at least an epsilon away from P. And that's going to make it so that it's impossible to find a further subsequence that converges to P, which will be the contradiction. It's going to contradict this first statement that we had here. So try to fill in the rest of the details of that. That one might take, a little while to wrap your mind around all the things that are going on. That's a great problem. And then there's something here that is great. This is one of the last things in this, is to show the necessity of a common limit point in there. Show that in the statement any subsequence has a convergent subsequence implies that Pn converges is not necessarily true. And so a problem that you've seen, maybe on page 2 of these lecture notes, is a very useful example here. So, all right. That is, I believe, that's the last page of these notes. So that's it. Thanks for listening. Fairly short recording, and I'll see you in class.